of the sun, solar system, and its impact on the Earth. In this webinar, you will gain valuable insights into the mission's objective and its potential implications for the scientific research and space technology. We have two experts with us, Dr. Rintu Nath and Dr. Kinkini Das Gupta Mishra. Both are senior scientists in Vigyan Prasar. The first lecture will be delivered by Dr. Rintu Nath. Welcome, Dr. Rintu Nath.
Good morning.
Your voice is not audible, sir.
Is it audible now? Can you hear me?
It's audible now.
Yeah.
So over to you, sir. Thank you.
You need to give me the control for uploading my presentation.
Okay, we will make you co-host.
Right. No, I don't have control yet.
A few more minutes, please.
Okay.
So this webinar is exclusively organized for our esteemed WIPNet members. So, is it able? You are able to do?
Right.
Yeah. Okay. Over to you, sir. Thank you very much.
Good morning. So today we'll be discussing about the Aditya-L1 mission of ISRO, which is scheduled to happen tomorrow. And in my lecture, I'll take you to a small presentation, which I prepared for you to tell you why we need to study about sun, why it's so interesting, why we need to do that, what are the interesting facts, what we're trying to achieve with this Aditya mission. So let me start with my presentation first, and I'll have about 15-20 minutes presentation, and if there are questions, I can take that also. So let me share my screen. Okay, is it visible?
Yeah, it's visible, sir.
Full screen?
Yeah, it's in the full screen.
Okay. So all of us know that why sun is so important to us. This is ultimate source of energy, whatever energy we are using, maybe the petroleum, other forms of fuels, but ultimately there's a source from the sun only. So we need to study the sun to better understand how it ever-changing conditions can influence Earth, other worlds, and even space itself. And the reason is the sun is very dynamic and is changing continuously, and there are many facts which is still not understood. For example, okay, there's a problem. Okay. There are unsolved issues like, that the temperature of the upper atmosphere of the sun is about 1 million degrees Celsius. Whereas its surface temperature is only 5,730, roughly 6,000 degrees Celsius. In fact, the core of the Earth is having the same temperature, even more than that. So surface temperature of sun is the temperature which the Earth core is having, whereas its outer atmosphere temperature is about 1 million degrees Celsius. This is very strange. And another important fact is that it's not really understood exactly how sun's radiation affects the dynamics of Earth's atmosphere. We know we have some understanding on that. It's finding a bit difficult to move this. Okay. As I said, that the temperature of the outermost corona is about 1 million degrees Celsius. This is mostly known as coronal mass ejection, CME. Thus, the explosions of sun causes these flares, and CME can cause very high energetic particle, millions of tons of very hot electrified materials to be expelled, and sometimes they are on a collision course with the Earth. Most of the time, we do not realize it. Because of the Earth's magnetic field, it gets diverted. But eventually, there are some way that it actually penetrates to the Earth's magnetic shell near the pole. Okay. So this is a rough, that my right hand side, there's a rough, not to scale diagram to explain. Whenever this coronal mass ejection happens, CME happens, there are particles. This is not only electromagnetic radiations alone, there are charged particles also, but mostly the radiations, they travel through, and the distance, is about 15 million kilometers. And they try to interact with the Earth's magnetic field. On the right-hand side, you can see that light blue shade is the Earth's magnetic field, where the center, absolutely center, is a small dot like it's the Earth. Again, not in scale, really. It should be actually smaller than that. So they interact. And the boundary where the solar material meets the magnetosphere is called the magnetopause. So there's something like an imaginary boundary which is protecting the Earth from the sun's flare. Although sun is very important for all source of energy, but still these harmful radiations need to be protected, and we are protected by this magnetosphere. And where this interaction takes place, still it penetrates into, and we see this colorful aura. This is northern belt, it's known as aurora borealis, and the southern light is known as aurora australis, because of the Australia's proximity. Although it looks very brilliant at dark night, but this is actually the interaction of sun's particles with the magnetic spheres of Earth, where it is actually penetrating through. All of us know about sunspots, although this looks dark, but actually they are the high energy particles. These sunspots are basically the cause of that CME, coronal mass ejection. There are some interesting parts in this. The number of sunspots, they actually have a cycle. And solar cycle, it follows a solar cycle. A strange thing happens in 17th century for a period of 70 years, and it was observed during 1640 to 1710. One British astronomer actually related it. He realized that this period where there was no sunspot, that about 70 years, it coincided with the absence of aura in the Earth. That means that interaction was much lesser, so there was no aura in the Earth, in either of the poles. And also, it was recorded that Earth suffered a slight decrease in temperature during this time. And it is actually known as Little Ice Age. So we can understand that any activity in sun is so important, which affects Earth. Now, of course, sun affects our life in everyday situation, because we have hundreds of satellites orbiting the Earth, both scientific and commercial use. Commercially, they're used also for telecommunication purposes. And events like coronal mass ejection, CME, from the Earth can affect their performance. And the more energetic particle can actually travel through the surface of the satellite, and it damages its instrument. And there's something more. whenever this geomagnetic storm happens, that is solar flares, which is magnanimously higher, can actually reach Earth in about 30-minute time. And that time, Earth's atmosphere gets heated. And the increased drag in the satellite is felt. You know what happens with this increased drag in the satellite is felt is actually the satellite can go to a lower orbit. It can lose altitude. And that's why the mechanism is required, so that this satellite can be again pushed to its own stable orbit. Otherwise, the satellite will actually fall down. So these are very important on an everyday aspect. And there's a chance for those kind of radiations if it penetrates through. It doesn't happen always, but we need to know what is the time. Is there a sequence? That's why it's so important to understand the sun. We can actually get radiation when we're flying in a commercial aircraft, which is at higher altitude. There's a possibility. Don't be afraid, but there's a possibility. And actually we get some radiations, but those may not be so harmful because the gamma ray radiations do not actually reach us, and X-rays also do not reach us. But the storms may cause some radiation to reach us. Some facts about the sun. It has layers. Sun has layers, and I'm not going to enter this sequence because that's not important for this presentation. But entirely unlike Earth, it is entirely gaseous and it rotates. It's roughly, it says 26 days, but the 26 days is not everywhere. Like near the equator, it's about 26 days. Near the pole, the sun, it takes about 35 days because of the gaseous natures of the sun. These dynamics also are required, important to understand the sun's characteristics. So I've just written some reasons why we need to study the sun stretch continuously. Of course, we do study sun, but why Aditya mission? Why it need to do it continuously in a particular point? There's required. The requirements are a unique laboratory to test our theories of evolution and other stars, formation in the galaxies. And with the sun, it is possible to study physical presence in the way that is impossible with more distant stars and atmospherical objects, because sun is easier to study because it's nearest to us. When nearest star would be much more far away, so that any feasibility of studying it almost ruled out. Solar studies have enabled us to determine that other stars also have spots and hot corona, because they do have, and how it affects on everyday life. If there is a frequency, is there any similarity? It's the most powerful particle accelerator in the solar system, accelerating ions up to giga electron volt and electrons of hundreds of mega electron volt. Now I'm coming to the Aditya mission major science objectives. Whatever I said till now, that coronal mass ejection is very important to understand its dynamics. So that's why one of the most important science objective is study solar's upper atmosphere, that is chromosphere and corona, its dynamics. Study of chromospheric and coronal heating, physics of partially ionized plasma, initiation of coronal mass ejection and flares. Observe the in situ particle and plasma environment, providing data for studying the particle dynamics from the sun. So there are two things. One is observing in the visible range. There's only the electromagnetic waves which is coming. At the same time, the coronal mass ejection will also entail energetic particles. So there are total 7 payloads in Aditya. 4 will be actually studying the radiation alone, whereas 3 will be actually doing in situ particle and plasma environment data. Physics of solar corona and its heating mechanism. Then the 5th is diagnostic of coronal and coronal loop plasma. You can see at the right-hand side, there's a coronal loop plasma, the diagram. Velocity and its density. What is the velocity and its density? Development, dynamics, and origin of CMEs. What does it mean? Is there any periods? Is there any sequence? Is there time frames where the coronal mass ejection takes place? Because that's something which is very interesting and also frightening at times. Identify the sequence of processes that occur at multiple layers, as chromospheres, base, and extended corona, which eventually leads to solar eruptive events. So the solar eruptive events are something we are worried. Magnetic field topology and magnetic field measurements of the solar corona. Because of this advantage point of Lagrange's point 1, it will be able to actually continuously look at the sun and will be able to do these measurements and drives for space weather, origin, composition, and dynamics of solar wind. So these are the major science objectives. There are some uniqueness of Aditya-L mission. I can explain it, but maybe a small, because it's not really part of this presentation. Of course, it's the first time it will resolve in the UV band. And CME dynamics close to the solar disk, it's about 1.05 solar radius. What is it? 1.505 solar radius. Actually, this Lagrange's point L1 and it will be actually parked there around this halo orbit around this. It will be able to see if my cursor is movable. This is about 1.05 radius. It will be able to observe from here to this. So because this halo orbit will be able to do this, remember, it's not the exact distance. It is basically, this is angular distance, because you are at a distance about 1.5 million kilometers from the Earth, and whereas the sun and Earth is about 15 million kilometers. But if you see the angular projection, if you take it, it will be able to cover the disk from here to about 1.05 to this continuously. That's something unique that Aditya mission is going to offer. And there's onboard intelligence to detect CMEs and solar flares for optimized observation and data volume, because it will be continuously, because they will not be affected with any eclipses. There is no other celestial bodies going to come because of this advantage position. It will be able to gather data continuously, so it will be able to detect if the CME happens, is there in a sequence. And directional and energy anisotropy of solar winds using multi-directional observation because of this payloads it's having. So this is the first space-based. I have underlined space-based and observatory class. Space-based because of the observation will be happening from about 1.5 million kilometer distance from the Earth. That's why space-based. And this observatory class. What does observatory class mean? See, we have the observations, multiple observations, different mode of telescopes and X-ray range, UV range, and visible range. But this observatory class, making it observatory class that is a high precision, is a bit difficult. So this is the first time Aditya-L1 mission will have an observatory class. That means as if an entire science lab is as a payload of the Aditya. That's the observatory class. So it will be high precision. Basically, observatory class means you can say high precision, high data, high volume of data. It will be able to gather and also analyze. That's why it's called observatory class. The spacecraft is named to be, is a plan to be placed in halo orbit. I said, what is halo orbit? I'm coming a bit later. Around the Lagrangian point L1. What is Lagrangian point? Let's come to the next one. See, this is the second diagram, this below. See, this is the Earth here, and this somewhere here is the sun, not to scale. Because of the gravity, there are two objects, two massive mass, sun definitely more, and the Earth here. So somewhere in this point, which is near the Earth, the gravity pull of Earth and gravity pull of sun will almost balance. Remember, it's almost balanced. It's not exactly, because there are influences of other celestial bodies also, but it's very, very minimal. So we can neglect it. Even the sun and moon is there. So this is a point where it will be having almost like no gravity. So here, if you want to put it here, it's very easy for it to observe without wasting much of a fuel. Remember, it is not a single point. If you want to place it exactly at the single point, then you have to waste a lot of fuel on this to stabilize it. Why? Because the rotational motion, the sun is rotating, Earth is rotating, there are other celestial bodies which is rotating. So it's not really a point, exact point, Lagrange's point, where that's Aditya is going to be parked. You can park it, but it's unnecessary to park it there because of the wastage of too much of fuel. So it will be actually revolving like this. So it is calculations like this. This path will be like this. Any rotational motion needs some centripetal force, and the centripetal force will be exactly equal to the net gravitational pull by the sun and the earth. So that's what is the idealistic situation. So this is a Lagrange's point. There are basically 5 Lagrange points. Here I've shown in the upper one, this is L1, which we're talking about. Aditya will be here, and this is halo orbit. Then this is L2. L2 is the other side of the sun. If it's not all the time this side. If our sun goes and Earth goes the other side, L2 becomes. Then this is L3, the other side of the sun. And L4 is not here visible. This is actually somewhere here, right side. And then this is, I think you are able to see. I'm not able to see because of the screen. So it's somewhere at the right side, and this L5. L4 is almost opposite to L5. So this is L5. There's a 5 Lagrange point. So the path followed by satellite or spacecraft, Aditya will be talking about the spacecraft, although it will be behaving more like a satellite, but we are calling it a spacecraft because it will be actually traveling about 1.5 million kilometers from the Earth, and it will be towards that, measuring in that halo orbit. So it's not really orbiting either of Earth or Sun, but it is orbiting a small radius elliptical path. So we're calling it a spacecraft. Sometime, if the application calls, as I've said, you can actually place it exactly at the point, but it's not required here. And this is somehow kind of a path which will be this Aditya mission will be following. This is right hand side dot is the Earth. Don't be confused with this bigger Earth. Bigger Earth is just to give you a kind of a scale, because if this is a Lagrange's point and this is a halo orbit, then the Earth is actually bigger than that. But for the time being, consider there's a dot, small dot is the Earth, and it will have, all of it will take multiple loops after it, or PSLV places it in the lower Earth orbit. It will have a multiple loop. Then there will be a slingshot here. At this point, there's a slingshot, and it will go to this cruise phase. It will go towards the sun, and then about 1.5 kilometer, it will take this halo orbit, which is that L1 is the Lagrange's point. So this is about the entire plan for this Aditya mission. And these are the payloads. As I said, there are total 7 payloads. There are remote sensing payloads, 1, 2, 3, 4. Most important part is this VELC. This is a visible emission line coronagraph. This will actually do this corona mapping images and spectroscopic analysis of VELC. I'm not going into detail of this. I'm sure that this will be anyway available, and my next speaker will be talking about some of these payloads. So there are total 7, 4 are for this imaging purpose, and the 3 is the in situ particle analysis, and it will be able to see that how the solar wind and the particle and the protons and heavier particles in which direction it goes. So there are 3 more. And this will be taken by the PSLV Excel tomorrow. It is all set to do. And we're going to be waiting for this to take place tomorrow. And I'm through with my presentation. If you have a question, you're welcome to ask me.
Thank you. Thank you, sir.
Yeah.
So one question from the participant: up to how near the sun will be reaching this time?
See, as I said, this from the Earth, sun is about 15 million kilometers. So Aditya will be going about 10% of that, 1.5 million kilometer from the Earth. And it will be actually in a Lagrange's point L1. That's why Aditya-L1 mission, because there's a point which will be at equilibrium where gravitational pull of the sun and the Earth will be nearly balancing it. And it will be orbiting through that L1 point in an orbit which is called halo orbit. So about 1.5 million kilometer. Yeah, that's the answer.
Yeah. And another was how this mission is going to help India in space program, because we have successfully completed the Chandrayaan-3.
Right.
So how this mission will go?
Chandrayaan mission and this Aditya-L1 mission are entirely different. Chandrayaan mission is more on showing the technological supremacy that we are having in a soft landing, and of course there will be in situ scientific experiments. Whereas Aditya-L1 mission is mostly scientific heavy, I should say, because technologically we have already achieved that fate of and PSLV we have launched several times. It's something like actually this Aditya-L1 mission is something like lifting satellite. Although we are calling it as a spacecraft because it will be about 1.5 million kilometers from the Earth. But why it's important? That's what actually was the first part of my presentation I have covered. That it's very important to study sun. And continuous study of sun for this, especially this coronal mass ejection, CME, and its radiation and its effects on Earth is very important. And somebody or the other it has to do. It's not that we are the first time we are doing it, but from India, yes, we're the first time we are doing. And there are some uniqueness in this Aditya-L1 because of the uniqueness that it will be able to do cover about 1.05 Earth sun radius. It'll be able to see the trajectory of the coronal mass ejection. What is the radiation? And if in situ experiments are taken, the particle acceleration, their charge, and their periodicity, their intensity. So there are 7 payloads. So out of which 4 will be actually for the radiation and 3 are for the in situ scientific experiments for the particles, which is very unique for this Aditya-L1 mission. So that's very important for not only for the for India, it's for the whole world to study sun and to get new insight on sun.
Great. Another query, like how many payloads will be Aditya-L1 carry? And what type of
7 payloads, I have already said.
7 payloads you already told. And what type of instruments will the payload use?
Yeah, it is already given in my experiment. This slide.
Can you just elaborate once more, please? Because we got query from them.
So these are the 7 payloads. First one is visible emission line coronagraphy. This is the most important part. This is the first and most important VELC. This Indian Institute of Astrophysics has designed it, IIA. Then solar ultraviolet imaging telescope, SUIT, SUIT, and then solar low energy X-ray spectrometer and high energy L1 orbiting X-ray spectrometer. And this, apart from these 4, there are in situ payloads. As I said, there's the particles to determine the particles and its acceleration and velocity and the intensity. Aditya solar wind particle experiments, then plasma analyzer package for Aditya, and then advanced triaxial high resolution digital magnetometer. So these are the 7 payloads. So remaining 5, 6, 7 are for the in situ experiments, and the first 4 are for radiation determination. And it is important that whenever we do X-ray spectroscopy using X-ray spectrometer, it's important that we go beyond the Earth's atmosphere, Earth's boundary. That's why it's very important that X-ray spectroscopies are always done outside the Earth's atmosphere. Right.
So we get another query. Few queries are there. So how do you compare ISRO Aditya-L1 with Parker probe of NASA? Earlier too, there were parallel drawn between lunar probes when Chandrayaan 3 was on its way to success.
See, this mission objectives are different. The Parker probe mission objectives and Aditya-L1 mission objectives are different. Aditya-L1 is mostly concentrating on CME, that's coronal mass ejection, its periodicity, its intensity, and also it is having that in situ payloads of this serial number 5, 6, and 7, which will be actually concentrating on the particle accelerators, accelerations, and its intensity. Another important difference is that the CME mass ejection, it will be doing at a distance of angular distance of 1.05 solar radius, so which is not done by Parker. So 1.05 mean if we take this solar disk, just let me take it. Yeah, this is angular distance. If you at a distance towards me, say this is the sun and it's towards me. From me, if I take a this small button, this sharp button, and if I place in front of my eye, then I'll be able to guard the sun entirely. This is angular projection. So because it's at 1.1 about 1.5 million distance from the Earth, and from the sun is actually much on a larger distance, about 10 times of that. When it's in this halo orbit, even if it is moving this from here to here, actually we are able to cover from the entire radius. And entire radius, when you are covering and CME mass ejection, you are continuously observing, that's something unique. Aditya mission will be able to do it. Yeah, because of its advantage position of L1.
Okay. So shall we take a few more queries?
Yeah.
Okay.
I think I have done my presentation in lower than that what I was given time, so I can take more questions. Yeah.
Okay, thank you. If Aditya-L1 is not able to catch a targeted orbit, is there any backup for the? Is there any backup plan?
See, this is I think something backup plan is ISRO to decide. I'm not aware of that. But as I said, this is Aditya-L1 mission is unlike Chandrayaan mission. There is no tensed and those sequences of we need. It is something like the satellite payload. although we're calling it as a spacecraft, but it's something like satellite payload, and PSLV, I think done, dozens of such payloads upliftment. So I don't see any of these, scopes of delaying. It's something like we thought about Chandrayaan soft landing. There is no such scope of that. So I don't know whether it's plan B or not.
So similar question, I think I can say, will these missions help India becoming a global player in the space industry and bring foreign direct investment for betting economic opportunities, or these are only academic and new technology pursuits?
See, economic opportunities, and when you say this space economy, people are talking about, without presence of science activities and science experiments, those will be futile and non-sustainable. First, let us understand it is linked up. So if you see my presentation, I have already talked about that, why we need to understand sun, why we need, because we need to be cautious. We need to be planning our activities, especially related to the space science. And sun is the nearest star from us, so it's very important to understand a star like this, and also how to protect us because of the sun flares at times when there's a highly energetic particle which comes to us. And if we are prepared, if there is early warning system is at all possible. So this kind of studies, it's not only that India is going to get benefit, the entire world is going to get benefit, because once a sun particle reaches, it doesn't reach India targeting, it reaches everywhere. So this first part. And second part, yes, India is a major player in space now. We are at the same category of America, China, Russia. India is even come in that same bracket. And along with these, if we talk about that space economy, yes, we are in that race, although maybe we are not at that forefront of getting this full power of space economy. But by showing this, to the world that a soft landing for Chandrayaan-3 and the Aditya-L1 mission, kind of mission like this, definitely we have a positive say to the world that our space program is very advanced, and we are going to take part in a major way in the days to come.
Yeah, you talked about the flares which sun is regularly emitting. So will this flare is going to affect the Aditya-L1? And another thing, what is the unique about special advantage pointing at L1? You have already discussed, but the query is there. That's why
Okay. Yeah, see, this CME, that's coronal mass ejection, is dangerous. Yeah, it has a very highly energetic particle. If you or me are there at L1, we not only are going to get burnt, not directly, but because of the particles, radiations which will be reaching us, we'll be exposed to tremendous amount of X-rays and gamma rays. If you go to that Lagrange's point, L1 point, if we go there, but Aditya-L1 will have the these payloads will be actually tested and protected, and will be able to work with this radiation. In fact, their job is, 3 of their machines payloads will be actually detecting those high energy particles which will be hitting it, and it will have in situ experiments on that. So they are protected, they are well tested for withstanding that kind of heat and the radiation. So nothing to be worried about those payloads. But of course, we cannot go there. In fact, some of this part of that reaches us, and we see this nice auroras, aurora borealis, and in northern belt, and aurora australis in southern belt. Those looks nice, but not so nice if it hits us directly.
So this Aditya-L1 is going to provide any information about cosmic rays also?
See, cosmic ray is a very general term, actually. It's mostly it's talking about the flames and radiations, entire spectrum. Actually, sun is also a perfect black body, which gives radiation the entire spectrum of the electromagnetic radiation, starting from radio wave till this gamma rays. So this entire radiation, of course, it will be observed, but mostly the Aditya-L1 mission will be looking at more of the solar dynamics. This, it's coronal mass ejections, this periodicity. What is the particle energy level, and what is the intensity level? This is going to be. Cosmic ray is a very, very, very generic term.
So again, a generic question. what is the total budget, how much it's useful for future study. Already you have discussed. So do you
Future
want to
study,
comment
yes.
on-
Cost, budget, I really do not know. Even I don't know even whether it's very important to discuss about the budget. When you talk about the budget, it's not really the manufacturing cost. This involves so many other things, manpower, the scientists, and there are not only ISRO which is involved. I think that's where people do the mistake, because a lot of other, institutes, they are involved. So if you take about this, we do not consider this budget is as a foremost point of discussion. And of course, this Aditya-L1 mission, something like this is going to be beneficial for our understanding on the sun. And as I said, it's not for India alone, but India will be paved the way to sharing the data, and the whole world is going to be benefited. It's very important.
So you have discussed about the payloads also. I think our next speaker is going to talk about the payloads also. Meanwhile, some specific information Aditya-L1 payload is going to provide.
Yeah, all payloads are actually all payload. No, and what I'm saying, all the 7 payloads are for specific purposes. So none is redundant. All are required. BELC is the most important one, which will be actually talking about the coronal mass ejection and its periodicity and intensity.
So a few more questions are there. So will the Aditya-L1 be able to resolve global environmental condition after knowing about the sun characteristics? So, well, it's a study part. So certainly we are going to get help from the information which Aditya-L1 is going to provide us in near future.
So global environment is dependent on not only sun alone,
Not
but
on the sun
other multiple facts. We here Aditya-L1 mission is actually specializing and focusing on sun and how solar radiations and coronal mass ejections going to affect the Earth, and is there any possibility of knowing this early warning system if there is a solar storm? Because solar storms are at times it's a very, very highly energetic particle, and those particles can actually reach Earth in about 30 minutes time. So the 30 minutes time is good enough to actually get a early warning system. And if at all it don't be afraid. We are not going to get affected much on this, because it's not that sun is suddenly we know sun, because sun is there for 4.5 billion years, and we are also surviving for a million years. It's not that suddenly something is going to happen, but we need to protect our satellites from the sun, because satellites get affected, they get damaged, they may get damaged by these solar flares. And this is going to give us some early warning system.
Okay, so if L2 and L3 lies beyond the Earth and Sun, how is an object kept there stable? You have already discussed, because there's a point where pull is almost negligible. Won't it be
the question is whoever is asked, he is asking a typical physics question. Actually, nice question. Actually, I don't know who has asked this question.
This is called Neeraj Kumar.
Yeah, good. Very
so
good.
How is an object kept there stable? Wanted the subject to double pull?
Let me go to that. Go to that. Yeah, very nice question. Actually, I did not expect this question from. Let me just go through it. Yeah, this is. See, his question is very pertinent. Very good, Neeraj. Thank you. See, this is sun, this is Earth, and okay, their gravitational pull, because gravitational pull is always attractive. So sun is attracting here, this Earth is attracting here. How on earth this side is going to be stable? L2 Lagrange, that's the question. And L3, this is very good question. Yeah. See, I'm telling you now the reason. This is actually, it's not only gravitational pull, this is also gravitational potential. This is high physics here. The potential, at these 2 points, as well as these 2 points and L1, they try to be at the same level of potential. Okay. So whenever this is L2, it is not only this Earth rotation and sun rotation. See, what you are not understanding, they themselves are orbiting actually. Okay. The sun is orbiting on its own rotations. Earth is rotating on its own, and it's also the Earth is also rotating on its spinning motion as well as rotational motion. So these two together, this makes L2 potential 0 at times. It's not, see, all these 5 points are not stable, static point. They are dynamic. They keep on rotating. But this is a very good question. And remember, although we are talking about these 2 celestial bodies, sun and Earth, we should not forget this effect of other planets which is around. And because of the rotation, all these points are not exactly fixed. It keep on rotating. Yeah.
Well, What is the expected life of Aditya-L1 and why the name Aditya-L1?
See, Aditya is I think, it's a Sanskrit name of sun, and L1 is Lagrange's point. Okay, because it will be at L1 point, not in L2. Had it been in L2 point, it would have been Aditya L2. There's nothing like mission 2. It's mission 1. It's nothing to do with mission 1. It's L1 because of the L1 Lagrange's point. That's it. And that mission life, sorry, I really do not know what is the mission life. And I have not gone through it. It must be available, but maybe my next speaker or maybe Dr. Bharat Bhushan may answer this on behalf of me.
Another question, how the thruster will change the Earth's orbit to the sun's orbit? If there is no atmosphere, how the thruster will work?
How the thruster will work? No. It is a squeeze mode. See, I'm going back. Okay. See, from this point onwards, it leaves the Earth's gravity, and this is squeeze mode. So you don't need thruster for that. It goes because of the initial momentum. That's why it's called slingshot. From slingshot, it will give up initial push so that it leaves that Earth's this gravity, and then it cruises. It doesn't need a thruster. Thruster needs when it goes near this, when again it is coming under the gravity of some sun is a bit of more than Earth, and then it needs, this is where the thruster is required. Here, the course correction. And then it goes, and here again, because of the gravity pull of Earth and sun, they balance each other. So again, you don't need much of energy, but yes, thruster will be required to make it stable in this orbit. Otherwise, it will keep on destabilizing, and at one point, it will actually go towards the sun, and it will be lost. So thruster is not required in this cruise phase from here to here. Cruise phase is written.
Okay.
Okay, I think I missed one more question. If there is no atmosphere, how thruster works? See, the thruster doesn't. If you are actually giving your own, outside fuel, if it injects, it doesn't need air to bounce back, because see, there are two. I think somebody understands physics very well. Again, Neeraj, is it Neeraj? Who has asked this question?
It's some anonymous attendee.
Okay, good question. Because he or she is asking the Newton's third law. Newton's third law is every action is having equal and opposite reaction. But what we forget is not on the same body. It's two different bodies. So there are two bodies. One is this Aditya-L1, spacecraft, and the other body is actually the fuel, the thruster. So it actually thruster gives this side, so it gives the the first body the momentum this side, the other direction. That's how it works. It's not from the atmosphere where you are getting thrust. No, it's unlike the aircraft. Aircraft movement is different. Aircraft movement and spacecraft movements are different. You are mistaken there. But again, I appreciate that question. Bharat Bhushanji, very nice. You should appreciate this question. I think somebody is asking, actually trying to understand. No, they do understand physics very well. Yeah.
Yeah. So it's good to get questions from the people who understand physics, but it's also good to get questions.
Yes.
From the
I'm really happy when this kind of
so
many places, even the university audience, where this university research scholars are sitting, I don't see much of this kind of questions. Even I'm so impressed.
So it's great. Our DWIPNet team members are getting participated in this webinar and getting queries, which I think it's getting solved also. So we will move on to our next speaker.
Thank you.
So if you want to be there, you can be there in the panelist, or you can discuss later on also.
Sure.
So our next speaker is Dr. Kinkini Das Gupta Mishra. She is senior scientist in Vigyan Prasar. Ma'am. Sir, if you can make us because you are now host, if you can make us a host, you can make host.
Yeah. I'm trying to check it. I've minimized it, and now I'm finding it difficult to move things. Yeah, is it okay now?
Yeah, it's now fine. So welcome, Kinkini ma'am.
Yeah, good morning. Can you hear me?
Yes, we can.
Yeah, hi, hello.
Welcome, ma'am.
Well, thank you, Dr. Bharat Bhushan. And so should I start?
Yeah, please, ma'am.
So very good morning to all of you. Dr. Rintunath has already spoken in detail, scientifically, giving a lot of, giving the understanding of physics and science, but still, since I thought that the gathering, the audience would be more of the WIPNET Science Club members, so I would start from a very basic understanding of sun, solar system, and then gradually move to Aditya-L1 mission. So is it okay, Bharat, if I
Yeah, that will be wonderful, ma'am.
Yeah. So as you all know, friends, that India is set to launch its first class solar space observatory called Aditya-L1 mission tomorrow on September 2nd, 2023. And this will be another major milestone after Chandrayaan. And we all have witnessed very recently the stellar work by ISRO, Indian Science Research Organizations, the landing of Chandrayaan-3 on the south pole of the moon. And now within a gap of 10 days, ISRO is ready with a maiden mission, Aditya-L1, to study the science of sun. And in making India a leader in space exploration, technology, and overall put together space sciences. And we have not made any such mission earlier to study sun. So today we will be talking more about the Aditya-L1 mission. But before we get on to that mission, no details, much details have been already spoken by my predecessor speaker. I'll start with sun, the solar system, why we need to study the sun, and then come over to the Aditya mission. I'm just sharing my screen. I have a presentation. Is my presentation visible?
Yes, ma'am.
Yeah.
You put it in the full screen mode. Yeah, it's now visible. It's in the full screen mode.
So these are very basics of our science, physics, and astronomy. Then there are many planetary systems like ours in the universe, with planets orbiting a host star. Our planetary system is called solar system because we use the word solar, as somebody asked, that to describe things related to our star, that is the sun. And our planetary system is located at the outer spiral axis of the Milky Way. And as you all know, that the Milky Way is a collection of hundreds of billions of stars, and the sun, our solar system star, is one of those. The Milky Way is considered to be a spiral galaxy, and in the center it lies a bright collection of older stars called the galactic bulge, and the disk contains spiral arms made of young stars and nebulas where active stars formation is taking place. And this is very basic and general, that our solar system consists of our star, the sun, and everything bound to it by the gravity. The planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, and dwarf planets such as Pluto. Besides this, there are dozens of moons and millions of asteroids, comets, and meteoroids. And the gravity of the, beyond our solar system, we have discovered thousands of planetary systems orbiting other stars in the Milky Way. Now coming to star, why we need to study sun? Our sun is the nearest star and the largest object in our solar system. The sun's volume would need 1.3 million of Earths to fill it. Its diameter is about 1.4 kilometers. The gravity of a sun holds all the objects of the solar system together, and keeping everything from the biggest planets to the smallest bits of debris in orbit around it. And as we all know, our sun is around 4.5 billion year old star. It is a hot glowing ball of hydrogen and helium at the center of our solar system. The distance to the sun from Earth is about 150 million kilometers, and it is the source of energy for our solar system. Without the solar energy, life on Earth, as we know, cannot exist. This star is so near to us that we can see its minutest surface details, because its warmth keeps the planet alive, and it is the most important star for the mankind, and every detail is worthy of observations and study. A sun's layers and atmosphere. Just like like our planet and most other celestial bodies, the sun is divided into distinct layers. And the critical difference is that the sun is not solid, unlike Earth, so the layers are a bit harder to determine. Because the sun is mostly composed of helium and hydrogen, and it is not solid, it does not have an outer boundary that is clearly defined. And however, we can determine the internal structure of the sun, and that is made up of several different layers. And it can, from the inside to out, the solar interior consists of the core, which is the central region, which is the hottest part of the sun, which is at the central region of the sun, and the temperature can reach as high as 15 million degrees Celsius. And at this temperature, a process called nuclear fusion takes place in the core, which powers the sun. And the visible surface of the sun, which is known as photosphere, is relatively cool, and temperatures of about 5,500 degrees centigrade. We'll come to that later. So finally, we have the core as the innermost layer of the sun, and the core is plasma. Its movement is extremely similar to that of a gas. And this releases, in the core, as I said, nuclear reactions occur that create helium from hydrogen atoms. And this releases huge amounts of energy, and it starts to move towards the outer layer. And this energy eventually becomes the light and heat that we receive on the Earth. Second is the radiative zone, which extends outward from the outer edge of the core to the base of the convection zone, and which is characterized by the method of energy transport radiation. And this is the second inner layer. The radiative zone is the second inner layer of the sun, and it sits outside the core, and it holds its extremely high temperature. And this layer serves as a passage for all the energy that is released by the core. And then the next layer is the convection zone, which is the outermost layer of the solar interior, which is extending from a depth of about 200,000 kilometers to the visible surface, where its motion is seen as granules and supergranules. So there are three layers of the sun, the inner layers of the sun. The convection zone is the outermost. It completely surrounds the next layer, the radiative zone, after which we have the core, the innermost layer of the sun. And now we come to the outer layers of the sun. There are four outer layers of the sun. The corona is the outermost one. The outer layers are the photosphere, the chromosphere, transition region, and the outermost is the corona. The photosphere is the visible surface of the sun. The photosphere is the lowest layer of the sun's atmosphere, which we can observe directly. And that the term photosphere means sphere of light, and it is the layer where most of the sun's energy is emitted, and it takes about 8 minutes for sunlight from the photosphere to reach Earth. And it is that part that we see shining. And next is the chromosphere, which is an irregular layer and which is above the photosphere, where the temperature rises from 6,000 degrees centigrade to about 20,000 degrees centigrade. And this is the temperature, the chromosphere is not as hot as other parts of the sun, and it glows red, which is followed by transition region, which is a thin and very irregular layer of sun's atmosphere that separates the hot corona from the much cooler chromosphere. And this layer marks the spot where temperature rises tremendously, since the corona layer is much hotter than the chromosphere. Then the outermost part of the sun's atmosphere is the corona. It is known as the sun's halo or the crown, where the temperature it is much hotter than the photosphere, and the corona extends millions of kilometers into space, and it is usually hidden by the bright light of the sun's surface. That is why it makes it difficult to see corona without special instruments, or it is impossible to see the corona with naked eye. And we are able to see during a solar eclipse or by using a special device called a coronagraph. And there is no upper limit to the corona. So the photosphere is part of the sun that we see shining. The chromosphere is an active layer that glows red. And the corona is the halo around the sun. Why do we study sun? The science of studying sun and its influence toward the solar system is called the heliophysics. And from our vantage point on Earth, the sun may appear like an unchanging source of light and heat in the sky, but the sun is a dynamic star and constantly changing and sending energy out in the space. So it is made up of super hot ionized gas called plasma. And since sun is the nearest star and therefore can be studied in much more detail as compared to other stars. And by studying the sun, we can learn much more about the stars in our Milky Way, as well as about stars in various other galaxies. Occasionally, the sun gets angry. When it gets angry, it shows several eruptive phenomena and releases immense amount of energy into the solar system. And the sun releases energy in two ways: the usual flow of light that illuminates the Earth and makes life possible, but also in more violent and dramatic way. And it gives off bursts of light particles and magnetic fields that can have ripple effects on the way out to the solar system's magnetic edge. If such explosive solar phenomena is directed towards Earth, it could cause various types of disturbances in the near-Earth space environment. And these eruptions can be so large that can reach our planet and cause serious damage by disrupting our satellite system and our power systems, other communication devices. Our TV may not work, our cell phones will be down, and even suppose a high-speed train may run loose. And if an astronaut happens to be on the moon at that time, when the sun erupts, he or she would be in great danger. Therefore, we study the sun to better understand how is ever-changing conditions can influence Earth, other worlds, and even space itself. There's something called space weather. The activity on this Earth's surface, the sun's surface, creates a type of weather called space weather. And the sun is really far away, 150 million kilometers from Earth. However, space weather can affect Earth and the rest of the solar system. The space weather refers to the changing environmental conditions in space in the vicinity of Earth and other planets. We use more and more technology in space for understanding space. Weather is very important, and also understanding near Earth space weather sheds light on the behavior of space weather of other planets. The sun is always spewing gas and particles into space. This stream of particles is known as solar wind. The gas and the particles come from the sun's hot outer atmosphere, that is corona, and these particles from the corona are charged with electricity. The solar wind carries these particles toward Earth at up to 1 million miles per hour. So this is the space weather, and the eruptions lead to solar activity, which includes such phenomena as sunspots, sun flares, prominences, and coronal mass injection. So that is why we need to study sun, and that is where the Aditya-L1 mission is, India's first solar mission. The ISRO will launch Aditya-L1, the first space-based Indian observatory to study the sun, and this will be India's first solar mission. Aditya-1 will be launched using PSLV-XL from Sriharikota, Andhra Pradesh, and it will travel to a distance of 1.5 million kilometers away from Earth and observe the solar activity. What is its objective? The main objective of Aditya-L1 mission is that it will help in tracking Earth-directed storms and predict its impact through solar observations. It will study the sun's outermost layers, the corona and the chromosphere, and collect data about coronal mass ejection, which will also yield information for space weather prediction. These are some of the major objectives and uniqueness of Aditya-L1. Basically, get a deeper understanding of the sun. First time, specially resolved solar disk in the UV band, the ultraviolet band, the coronal mass ejection dynamics close to the solar disk, thereby providing information in the acceleration regime, which is not observed constantly. So there will be, these are some of the uniqueness of the Aditya-L1. The spacecraft named after the sun's core will not actually go to the sun. It will travel 150 million kilometers from Earth to the L1 between the Earth and the sun. This distance is nearly 4 times that traveled by Chandrayaan mission. And the position of the satellite, the position of the aircraft, in order to get the best signs from the sun, continuous viewing of sun is preferred without any occultation or eclipses, and hence Aditya-L1 satellite will be placed in the halo orbit around the Lagrangian point L1 of the Sun-Earth system. So the Aditya-L1 spacecraft will be carefully positioned within a halo orbit around the Lagrange point L1 of the Sun-Earth system, which is about 1.5 million kilometers from the Earth. And it is expected to take more than 120 days for the spacecraft to reach the L1. Dr. Nath has already discussed much in detail about the L1 Lagrange points. For a two-body gravitational system, the Lagrange points are the positions in space where small objects tend to stay if put there. This strategic location is important, and it is in between the Earth and the sun. And by being stationed in this unique orbit, the satellite will have a remarkable advantage, an uninterrupted and continuous view of the sun, free from any disturbances, occurrences of occultations or eclipses. And this exceptional vantage point offers an unparalleled opportunity to closely observe solar activities and their impact in space weather in real time. And this is the Lagrange points. The Lagrange point L1, as I've said, it is located around 1.5 million kilometers from the Earth, and movement in the halo orbit around L1 point will let the satellite to continuously observe the sun. Because of this, scientists will be able to observe the solar activities and its effect on space weather in real time. And Lagrange L1 is among the 5 Lagrange points in the Earth-Sun system. At this point, the gravitational forces of the two bodies balance the centrifugal force felt by a smaller object, and due to the balance of force, the object is not attracted by the sun. Hence, it would be able to effectively hover in a stable position to the two larger bodies, and this means satellite placed at the Lagrange point L1 do not need to use a lot of fuel to remain in this position. And the distance will be covered, as I've already said, in 4 months, and the spacecraft will be inserted into a halo orbit around the L1 point, and it will collect data as it has been informed or told to for 5 years. And keeping in mind the gravitational forces of the Earth and the sun, the Lagrange point L1, which is located between the Earth and sun, which is about 1.5 million kilometers away from Earth, which is in the direction of the sun, this point is located on the line connecting the two bodies, and it is situated in the Earth's orbital path around the sun. Now, the trajectory of the Aditya-L1 is this, that it is at the spacecraft, as the spacecraft travel, it will be, once it is launched, it will go in a circular orbit first, then it will skilling a short, and then it will make into an elliptical orbit, and then after 4 such orbit enhancement, it will take on to a cruise phase, So the the L1 point, which is at 1.5 million kilometer away, it will take about 120 to 125 days to reach that point. So if you can see in the figure here, this is the elliptical orbit, then it takes a cruise path, and then it goes into the halo orbit and reach the L1 point. And it is designed to provide remote observations of the solar corona, the outermost layer of the sun. Using this, what kind of instruments the Aditya-L1 is supposed to carry? Due to limited mass, power, and volume of the spaces, Aditya-L1 will carry a limited set of scientific experiments. All the payloads of Aditya-L1 have been indigenously developed at different laboratories in India. It is in close collaboration with the centers of ISRO and the ISRO. The Aditya L1 mission will carry 7 scientific payloads to conduct a systemic study of the sun. And 4 of the spacecraft's payloads will directly view the sun, while 3 payloads will carry out in situ studies of particles and fields at the Lagrange point 1. What are the benefits of Aditya-L1? The spacecraft will have the advantage of continuously viewing sun without any occultation or eclipse. The data gathered from the mission will be used to improve our knowledge, the scientific study, and predict space weather events. In the case of Earth, the interaction of the Earth's magnetic field with the field carried by the coronal mass energy can trigger a magnetic disturbances on the Earth. By understanding the sun, we can better protect ourselves from these disturbances, these events, and we can, it will help us to understand all the science of sun, basically, and all the solar activities. These are the payloads that I've already mentioned, that there are 7 payloads on board to observe the photosphere, chromosphere, and the outermost layers of the sun. These are a visible line emission coronagraph, VLC, solar ultraviolet imaging telescope, Aditya solar wind particle experiment, plasma analyzer package for Aditya, solar low energy X-ray spectrometer, high energy L1 orbiting X-ray spectrometer, and magnetometer. And the Aditya-L1 is anticipated to yield invaluable insights for a variety of solar phenomena, such as the coronal heating, the mechanics behind coronal mass ejections, the behavior of pre-flare and flare activities, along with their distinguishing characteristics, as well as the propagation of particles and fields throughout the celestial expanse. The uniqueness of this mission has various aspects. First, the mission aims to acquire the first spatially resolved solar disk in the near UV band. Secondly, it will study the coronal mass ejections dynamics close to the solar disk, which would tell us about the CME regime when the ejection undergo acceleration. Third, there is an onboard intelligence to detect the CMEs and solar flares for optimized observations and data. Yeah.
Yeah, your slide
payload.
You can change the slide. Yeah.
Thirdly, there is an onboard intelligence to detect CMEs and solar flares for optimized observations and data volume. And finally, lastly, there is an intent to study directional and energy anisotropy of solar wind using multi-direction observations. And the significance of the mission is that the data from Aditya missions will be immensely helpful in discriminating between different models for the origin of solar storms, and also for constraining how the storms evolve and what path they take through the interplanetary space from sun to Earth. Thank you.
Thank you, ma'am. Thank you for your talk. And I think we can take few queries.
Yes.
So it's you have already discussed, and Dr. Rintunath has also discussed difference of other L points compared to L1 from L1. So if you can again differentiate between the other L points and as compared to the L1.
See, as I've already said, that because of this advantageous position for studying the sun, science of sun, the solar activities, the payload, the Aditya-L1 will be positioned at between the sun and the earth at L1 point, which is the Lagrange point, and it will, which is 1.5 million kilometers away from the earth. And so that is why the name is also Aditya-L1 mission. And the L1, L2 other points that is there are the other Lagrange points where right now these solar activities is not being planned by India or by ISRO.
And one question is that define payloads. What is the payloads?
So basically the payloads are basically they are the instruments, scientific instruments, and these are the, they are being sent to observe and detect all the specific requirements and the parameters of solar activities. So here, like in this case, there are 7 payloads. So there are 7, which contains the 7 scientific instruments, which are being sent to observe the certain activities of the solar, the sun, and detect the CME ejections, the coronal mass ejections.
So anything Dr. Nath want to discuss, because we have answered almost all.
Yeah, I think Dr. Kinkini has already replied on this Lagrange's point. There are 5. The question was like why L1 is advantageous. Already she has,
compared to another.
ISRO has already planned for L1. See, L2, L3, L4, and L5 also. This Lagrange's point is the point where you have the equilibrium. That the gravitational pull has been equal to the centripetal force required for the circular motion. Yes. So that both the 5 points have the same advantage. However, the L1 is number 1 is the closest. Number 2, it is between the sun and the earth. So it will have the uninterrupted view of the sun from the closest range possible. And that is one of the mission objective, that it will be having the CME to observe from 1.05 sun radius, which I've already explained it. That's how L1 is chosen. L2, L3, L4, L5 have this advantage of having that equilibrium gravity with centripetal force. However, L1 is having one of that advantage. Extra advantage is the uninterrupted view and the nearest to sun, nearest to moon, Earth. Right.
So I think it is a good blend of a technical detailing of L1 and the mission, and also the basics of the sun and our solar system. Thank you, Dr. Nath and Dr. Kinkini Dasgupta Mishra. So thank you very much, our WIPNet team members. And they have, okay, so one question, kindly send your recorded email. Okay, so this is a general question. Okay, another question has come. Nature of the orbit, which it would be describing.
What?
Nature of orbit, which it would be describing.
Yeah, it is called halo orbit. It is around this L1 point, which will have the minimum energy requirement. If it sticks to that, if Aditya sticks to that L1 point, then a lot of energy would be required to stabilize it at that point because of the rotational motion of both Earth as well as Sun. So it will be actually taking an orbit. It's called halo orbit, where it will have the lowest energy requirement. So it will be on its own almost, but at times there will be some energy requirement for stabilizing the orbit.
So I think no more questions are there. So thank you very much. Thank you, Rintunath sir, madam.
You're welcome.
Thank you for your time.
Thank you so much.
Thank you. So with this, we are ending this webinar. Thank you.
Sure.
Ma'am, you have to